Alright, so Chapter 5 is Boolean algebra and reduction techniques. In this part 1, we're going to get into writing Boolean equations for combinational logic circuits. We're going to use some laws and rules of Boolean algebra to simplify the circuits. We'll touch on DeMorgan's theorem, which is just another tool we can use to simplify these complex equations. We'll also get into just a little bit on the universality of NAND and NOR gates and how we can use them to implement other kinds of logic gates. And then also a little bit on sum of products expressions and how we can implement them using AND-OR invert gates or AOI gates. Not in this video, but in part 2, we're going to cover Carnot maps or K-maps and how we use those to reduce complex Boolean equations, and also some of the steps involved in solving complete system design applications. So to start with, when we talk about combinational logic, the term combinational logic just means basically using two or more logic gates to perform a more useful complex function, combining two or more logic gates to do something. Just as an example here, they give you B equals KD plus HD, or technically it's K and D ORed with H and D, but you'll find that I often abbreviate just to save time. So to reduce that, they've reduced it here for us already. We'll get into how they reduced it and the methods for reducing later, but just as an example here, they reduced it for us already. They reduced it down to B equals D ANDed with K plus H. So as an example, let's say you want a warning buzzer in your car to go off when one of two conditions is met. So this is just where they got the sample equation that we just saw. But the situation is we have a warning buzzer, and we want it to go off if one of two conditions are met, either condition 1 or, and that's where this gate comes from, or condition 2 happens. We want that buzzer to go off. Well, what's condition 1? Well, the first condition is if our key is in the ignition and the door is opened. So those two inputs going into an AND gate. Our second condition would be if the headlights are on and the door is opened, then that would be our second condition produced by this AND gate here. And then, of course, those two go to that OR gate that we mentioned. So that's the function that we want out of this. Well, that equation would give us this B equals KD plus HD. That would be the equation we got from this diagram shown here. But if we reduce it to this second equation where K is ORed with H first and then that quantity is ANDed with D, we get something that looks like this. So instead of 3 gates, now we're only using 2 gates. We just rearranged and simplified the equation so that now we have our inputs going to different kinds of gates, and we're only using 2 gates now, representing the same exact functionality, but in a simpler form. So that's why we learn how to reduce equations, to accomplish exactly this. So getting into the laws and rules. You will recognize, I'm sure, a lot of these laws and rules, particularly the first 3 laws that we're going to talk about from algebra class. They're not identical. Algebra rules or laws are not completely identical to Boolean laws. There are some differences between algebra and Boolean algebra, or regular algebra versus Boolean algebra, but you are going to see a lot of similarities. And so just getting right into it, the first law is the commutative law of addition and multiplication. In algebra, it would be addition and multiplication. In Boolean, of course, OR is represented by addition and AND is represented by multiplication. But almost identically to the regular old algebra, we have a commutative law that says the order of the variables doesn't matter. So A can be ORed with B, or B can be ORed with A. The order of A and B does not matter. And then similarly with AND gates, A ANDed with B is the same exact thing as B ANDed with A. Second law is associative law, also pretty much identical to regular algebra. You can, if you have multiple variables that are either ANDed together, or if they're all ORed together, but the point is that if they all share the same symbol, either the addition or multiplication symbol, it doesn't matter in which order you add or multiply them. So in the top case, we can add B and C, or rather, well, in Boolean, it would be ORing B and C first and then ORing that result with A, or we can OR A with B first and then OR that with C. In the second example, with the AND gates, we can AND B and C first and then AND it with A, or we can AND A and B first and then AND that with C. Doesn't matter, they're equivalent. Distributive law, the third law. This one also will look very similar to algebra, because this is just distributing, in the top example, we're just distributing A to B and C, or rather B plus C. The second example here, we're distributing using the, I don't know if you called it this in algebra class, but I call it the FOIL technique. The technique where we group, when we distribute, we group these variables first by the first variable in each set of parentheses. The first variable in this set is A. The first variable in the second set is C. So that's the first. Then the outside variables, meaning A is on the far left, D is on the far right. So those outside variables group together. The inside variables group together. And then the last variables of each set group together, B and D. And so distributing all of that, we get AC plus AD plus BC plus BD. So that is the distributive law. So with those three basic laws out of the way, there are also these other, it's basically a list of rules, and there are 10 of them. Technically 12 if you count the three variations of rule number 10, but starting with rule number 1 and rule number 2. And these first two rules have to do with when you AND things together with a definite 0 or a 1. First rule says if you AND something with a 0, it's always 0. Second says if you AND something with a 1, it always equals itself. Rules 3 and 4 are pretty much the same thing, just inverted because we're talking about OR gates now. But rule 3 says that anything ORed with a 0 equals itself. Anything ORed with a 1 is always 1. So then rules 5 and 6 have to do with things that are ANDed or ORed with themselves. So anything ANDed with itself is equal to itself. Anything ORed with itself is equal to itself. Rules 7 and 8 have to do with complements. So if you take any variable A and you AND it with its complement, meaning not A, it always equals 0. And if you take anything and OR it with its complement, it always equals 1. Rule 9, anything complemented twice will return to its original logic level. That kind of makes sense, you know, if you flip something once, it's upside down. If you flip it again, it's back right side up. You know, so taking A and we invert it twice, we just come back around to A. And visually, you'd be looking for double bars, where there are two bars stacked on top of each other over the same exact value. But don't confuse that with, let's say, this not A, and then there's, it's ORed with B, and then there's a bar over both of those. These two bars don't cancel. This is only applicable to when it's over a single value, or not even a single value, but if you had A or B, and you had two bars over the whole thing, the two bars here are over the same exact quantity, A ORed with B. So these two would cancel. So just be careful about canceling things that are technically over different values. So rule 10 is a little bit trickier. It's a little bit more just kind of you learn to recognize it. The first two are actually kind of similar. The first one says that anything, let's just call it A, ORed with a value where the opposite of A, meaning not A with a bar over it, and if that not A is ANDed with anything else, they're just calling it B here, but it could be anything else, we can basically eliminate the second A. And in a similar fashion, just inverted, if we have anything inverted, a not A, ORed with its complement, which in this case is just a regular A, and that complement is ANDed with B, then we can remove that second A. So basically, a value ORed with its complement, which is then ANDed with something else, we remove that second complemented value. And that's what those first two are basically saying. The third one, we're saying that anything ORed with itself, not its complement, but itself, which is then ANDed with something else, here we can actually just eliminate that whole second term. And we're just left with A. So those are the 10 rules. And here's just a summary of all of those laws and rules that we just went over. And it's just in a simplified equation form, but they all mean the same thing as what I just described. So, now getting to actually simplifying these logic circuits. The reason we do this is because we want to get equivalent circuits that can be formed with fewer gates. Doing it with fewer gates means the cost is reduced. It also means that the reliability is improved because we're using fewer gates, fewer parts to worry about. It's less complicated of a circuit. And we can do all of this using those laws and rules of Boolean algebra that we just went over. So getting into it, we'll take this circuit here. Now, they give us these three values here, these intermediate values, I can call them, just the intermediates between one gate and another gate before we actually get to the final, the result x. If they didn't give us these three values, I think it's a good habit to learn how to do this yourself. So let's just assume that they didn't give us these three values to begin with, and they just told us the ABC input on the left, then they drew out these logic gates, and then they just gave us this x value on the right as the output. So typically you'll want to start with the input side. In this case it's the left, but it could be the right. And we want to go from the input side to the output side, which the output of this circuit is on the right. So we're going this direction, and we'll start basically just figuring out what the output of each gate is. So for this first OR gate here, the inputs are A and B, so the result is A or B. And I think it's a good habit to write that down on each of these nodes. So when you figure out the output of a gate, write it down on that node that it's on, which is, this wire here. For this second gate, the inputs are just B, and then that's ANDed with C, so our result would be B and C. Write that down on the gate here. Writing it down helps us then to move on to this gate. So we take the inputs of this gate and AND them together. So we're ANDing this A or B here, and we're ANDing it with what? B and C here, right? So then that's our result for this node. So now we move on to this last gate, this OR gate. It's this whole value that we figured out here, ORed with just A, right? So we'll just OR that whole thing with an A. So now, I'm going to write out the equation real quick here. So now, we have that equation. X is equal to A ORed with B, which is ORed with B and C, which is then ORed with A. So that's our equation. So, where to start? The first thing I would notice is this parentheses here, and that we have a value outside the parentheses that can be ANDed. These two values are ANDed together, but that can be ANDed with this whole quantity here. And we can do that by distributing, using our law 3 of distributive properties. We can distribute this BC to A plus B. So that means we'll get ABC plus BC, and then don't forget our A to carry down here. So now we have that equation. The next thing I would notice is double letters. Those always stand out to me because it's so easy to simplify them. You see two of the same letters next to each other, that's a big red flag. It doesn't have to be two regular old B's. It could be B, or rather not B, ANDed with not B, ANDed with not B again. As long as, those individual values are identical to each other, we can cancel things out. And remember that anything ANDed with itself is always just itself, so we can actually just cancel out the duplicates, and we're left with just that single B. So now we have, let me just rewrite it, ABC plus BC plus A. The next step might not be as obvious because when we talked about the distributive property, we talked about, let's say that first step where we distributed the BC, we distributed out to values. But what is the opposite of distributing? Well, it's removing values, common values. Well, what values are in common here? I see that there's a BC here and a BC here. Those are common. So we can actually, in the reverse of our distributive property, we can actually pull out the BCs. Pull those out. Just like in algebra class, we are left with BC, and then we have parentheses because we pulled it out of those values there. If we pull BC out from this term, we're left with A. If we pull it out from this term, there was nothing, it was just BC there. But in algebra class, what would you do if you pulled out two variables from that? You would just represent it with a 1, right? Because you can think of this as B and C ANDed with a 1. Think of like an extra 1 sitting there. So that's what we're left with when we pull BC out. And then, of course, copy down the A from up there. Now, another red flag that should always stand out is when you see a 0 or a 1 somewhere, because usually there's a way to simplify it. Here we see A ORed with 1. And if we remember our rule, anything ORed with a 1 is always just a 1. So that means our equation is then BC ANDed with a 1, and then bring down the A. Well, what is anything, in this case BC, but anything ANDed with a 1 is always just itself, right? It's another one of our rules. So really, this 1 is gone. We are left with BC ORed with A, and that is our simplified equation. So just moving on to the next slide, where they go through that whole process that I just showed you, and they come up with x equals BC plus A, or BC or A, and then they just show the diagram of that there. We reduce that down to 2 logic gates. So now they have this equation, or sorry, rather this circuit, which they've given us those node values again. So actually, what I'm going to do is I'll skip the, going over each and every node and how they got these values, but we'll figure out what x is. We know that x is going to be equal to, so x is equal to this ORed with C. So we'll just copy that down. B, A, C, and then that is ORed with C. So that's our equation. And I will go ahead and write that down. All right. So now we have our equation written out. What to do first? Well, I see those parentheses again. I think I'm going to distribute that B to A and C. Push this up a little bit, actually. All right. So yeah, I think I'm going to distribute that B to the A and C. So we're going to get A, B, or BA. You can write it however you want because of that commutative property that we talked about. Doesn't matter the order, but we'll OR that with B and C, and then bring down our C from up there. So now we have this equation. One thing I see is there's a C here, and there's a C here. So we can do the reverse distribution and pull the C out. So we'll copy our AB over here, and that's going to be ORed with C. We pulled the C out. We're left with B here for the first term and a 1 here because the C was by itself. So now we have this equation. I see a 1 there, so anything ORed with a 1 is always 1. And then, of course, anything ANDed with a 1 is always just itself. So that 1 is gone. So now we're left with C, but remember to bring down this AB that we forgot about over here. And that is our equation. X equals AB ORed with C. All right, so, and that's what this slide is showing. So, and then there's the diagram at the bottom. That brings us to DeMorgan's theorem. So DeMorgan's theorem is another kind of rule. It has more to do with NAND and NOR gates, though. Actually, all to do with NAND and NOR gates. Here they show you just the equations, and I'll explain why exactly these equations work. But basically, it says that any quantity that's NANDed, meaning something ANDed with something else and then with a big bar over both terms, we can basically, you can think of it as splitting these two. Splitting A and B, flipping the sign to an and then splitting the bar in half. we're basically going from something NANDed with something else to something something's complement, or not something, ORed with not something else. In this case, not A ORed with not B. And then similarly for a NOR gate, we are going to break this up, and we're going to, instead of ORing, we're going to AND, and then the two values we're ANDing together are just the not A and then the not B. And be careful with that bar. It is separate. These are two separate terms. It means we're going to invert A first, and then we're going to invert B first. And then only after we've inverted both inputs, then we AND those results together. And to visually represent that, they have these diagrams here. Basically what we're saying is this A and B NANDed together is equivalent to, if we were to invert both inputs, invert A first, invert B first, indicated by these bubbles here. So we're going to invert our inputs first, and then OR them together, and that's the same output that we're going to see if we just NANDed them together. So as I said, you can think of it as changing the sign between them and then breaking the bar over them. Or in the reverse, if we go back to our other equations here, in the reverse, if we have these two values, let's say not A ANDed with not B, in reverse, we would, instead of breaking the bar, we would join the bar together as a single solid bar, and then we would flip the AND to an OR. So then, for this other example, we would, let's say in reverse, we would take these set of values here, we would join the bar, flip this OR to an AND. Just a dot, or you don't have to put the dot, but so two steps, going either way. Two steps are inverting the sign between the two. ORs go to ANDs, ANDs go to ORs, and either joining or breaking up the bar, whatever is the opposite. So going from a solid bar to a broken bar, or a broken bar to a solid bar. Be very careful using parentheses to maintain your proper groupings. You don't, especially in these more complicated equations, you might see a lot of parentheses, bars going over different things. You really want to keep track of your bars and your parentheses to make sure that you're grouping things properly, because in Boolean algebra it actually is very important to do that. Otherwise you're going to be barring something that shouldn't be barred, or parenthesing something you shouldn't be. So just keep that in mind when you're working on these. The result of this little conversion here into this these separate terms ORed with each other, it just so happens that the results of that gives us a sum of products form, meaning if we go back to this x equals not A ORed with not B, that is the sum of products form, meaning here's one product, here's another, and these could be ANDed with something else. Maybe there's a C here ANDed with the not B, but regardless, it's some sort of product. You can think of this A as ANDed with a 1 even. But we have a bunch of product terms, and they are all summed together using these plus signs. So here they're just showing basically showing something called bubble pushing, and I think they mention this in the next slide, but this thing called bubble pushing, which is you have this original circuit, And you'll notice that this is a NOR. So we're starting out with this kind of equation, right? X equals A NORed with B. And that's what this gate is doing. Well, we can apply DeMorgan's theorem, and we can turn this NOR gate into this gate equivalent. Basically inverting the inputs and making it an AND gate instead of an OR gate. And if we do that, which they show in this second circuit, we're basically moving our bubbles here. But you'll notice that the output here is bubbled, but then it's going to an input that's bubbled. So those inputs actually, those bubbles actually cancel out. And then same with these other two bubbles here. They cancel out. So now you're just left with 3 simple AND gates instead of 2 NANDs and a NOR. And then here they're just showing this bubble pushing idea. For inverters, obviously it doesn't matter too much. It's just a single input. So it doesn't matter if you invert it, at the beginning of this gate or at the end. It's just going to get inverted regardless. But for these NANDs and NORs, we actually flip the bubbles. So the bubbled input here flips to a no bubble at the output. And then the non-bubbled inputs of the NAND gate flip to bubbles. And when we do that, we also have to flip the AND to an OR. We have to flip it to the opposite gate. Same with a NOR. This bubble goes away. The 2 inputs get bubbles. We're basically just flipping the inputs and outputs bubble states. If it doesn't have a bubble, you give it one. If it has one, you take it away. So we flip the bubbles around, and then we flip our gate around from an OR to an AND. And this concept is called bubble pushing. So here they want us to write the Boolean equation for this circuit using DeMorgan's theorem. So because this isn't too complicated, I'm just going to go ahead and reveal the solution that they give here. So if we were to, first of all, if we were to figure out what the equation is, we would say, we would take this first NAND gate, and we'd say that it's A NANDed with B. So A, B with a big bar over it. And then this gate, the second gate, is that quantity, A NAND B, ANDed with, try and draw a dot, ANDed with just B. So that's the equation that they give you here. If we apply DeMorgan's theorem, we see that A NAND B. We apply DeMorgan's theorem, we break the bar in between A and B, so A and B have separate bars now, and then we flip the sign from an AND to an OR. So we get that OR symbol between them. And here's where you can put it in parentheses. It's actually probably a good habit to do it, just so you can keep track of what is actually being ANDed with this B here. B is actually ANDed with the quantity of this whole thing. So now that we have some big quantity in parentheses ANDed with B, we can distribute the B to each of those terms, and we come up with this equation here. Not A ANDed with B, and then not B, I kind of drew over the bar a bit there, but not B ANDed with B. Remember that anything ANDed with its complement, a B ANDed with a not B, is always going to be 0. So we convert that to a 0, and remember that anything, so for the second step here, anything anything ORed with a 0 is always just itself, so we can just eliminate the OR 0, and we're left with the simplified equation of not A ANDed with B, which is represented by this circuit here. And we see that the A is inverted first before it gets to the AND gate, and then it's ANDed with just a regular old B. And then we can actually, instead of drawing out the whole inverter to the AND gate, we could just put over here on the second circuit, we could just put a bubble on A to represent that it's inverted. So here, they want us to repeat that same thing for the circuit shown here. So if we were to, figure this out, we'd see that A NAND B here is ANDed with B NORed with C. And that's where we get this equation here. Get my pen out. That's where we get this equation here. So now we can apply DeMorgan's again. We're going to do it twice. We're going to do it on this A NANDed with B, this first term. Split the bar in half, flip the AND to an OR, and then for the second one here, we're going to break the bar between B and C, and we're going to change the OR to an AND. And then also note the use of parentheses to maintain proper grouping. It's where it's helpful to keep the parentheses there so you can see what can be distributed. If there is something that can be distributed, which of course there is, we can distribute the not B, not C to not A ORed with not B. And when we do that, we get to this first step here after we distribute. And then you'll notice not B and not B are both there, the same exact quantity ANDed with itself, so we can eliminate everything, but all of them but one. So we're left with the not B with the not C there. We'll notice that there's a not B, not C term there, and there's also one here. So we can reverse distribute, we can pull it out, and we're left with the not B, not C there, and then we're left with a not A on one side of the OR, and then a 1 on the other side of the OR, but anything ORed with a 1 is just a 1, and then that 1 would be ANDed with B, or not B, not C, so anything ANDed with a 1 is just itself, and that's where they get this equation. So, here is, at the top here, not B, not C. That basically just B and C inverted with an AND gate. Here is the bubble representation. We just have bubbles on the inputs of this AND gate. Well, we can actually remember DeMorgan's theorem again and go in reverse, and we can join the two bars together to a single bar, and then flip the AND to an OR to get a nice NOR gate. So when otherwise we would have had to use two inverters like they show at the top here, plus an AND gate, 3 different kinds of gates, now we can simplify to just a single NOR. All right, so for this example, it's a little bit more complicated, so I am going to actually manually write it out. But so I've pre-drawn it here. And we can start by figuring out our equation. In the diagram that they gave us on the slide, they already gave us what each of these nodes are, but we'll go ahead and just for practice go through each node. So for this node here, the output of this AND gate, what is this ANDing? It's just ANDing A and B together. For this NOR gate down here, the output is C NORed with D, the big bar over the top. So then the output for this AND gate, the middle AND gate, would be what? A and B ANDed with C NORed with D. And then this final NAND gate is basically this quantity here. I'll rewrite it here, actually. There's our quantity. NANDed with, so we're going to AND it first with A and B. I'll draw a dot just to differentiate the two terms, even though it's not entirely necessary, it just helps visually. But remember, this is a NAND gate, so we actually have to put a bar over the whole thing. So, there's our equation. That's all equal to x. So, first of all, we want to take care of the big bars first, because we can't really, we could try and, we could do the little bars, C NORed with D first, but I like to get rid of the big bars first so we don't have to worry about this whole massive quantity being under a single bar. So what I'm going to do is DeMorgan's theorem. We're going to split the bar right here, and we're going to flip this AND to an OR. So this half of the bar, this left half of the bar, is going to get its own bar. Remember to copy everything exactly, keeping track of the bars and which letters they're over exactly. That whole quantity gets barred. We're going to flip that AND to an OR, so now we write an OR, and then we take the right side of the split, which is just the AB, with a big bar over that. So we split that bar into two separate bars, and we converted our AND to an OR. So now we will, let's say we want to get rid of this big bar here. Well, we're just going to keep doing DeMorgan's. So we're going to split the bar here this time, and the left half would be just the AB with a bar over it, or basically just a NAND, and the right side of this split will be our C NORed with D with a big bar over it, but because this bar would be just over the parentheses value here, and then they were ANDed together, but we need to flip that AND to an OR now. And then, of course, copy down our other term from up there. Now the very obvious thing is this double bar. Two bars over the same exact value, in this case C ORed with D, cancel out. So now we just get C ORed with D, no bars. What we can also do with the other two terms, while we're at it, we can use DeMorgan's one more time. On this term here, we're going to split the bar. A is going to get its own bar, B is going to get its own bar, and they were ANDed together, so we want to flip it to an OR. And remember that whole quantity there was ORed with this quantity, C ORed with D, and this is going to be ORed with DeMorgan's applied to this set of variables here. We're going to split this off. Split the bar down the middle. A gets a bar, B gets its own bar. The AND flips to an OR. And we are left with that equation there. Now remember, each of these variables is now ORed with the other. They're all the same operation. There's no ANDs between them. It's just all ORs. Well, if you remember the associative property, we can move these parentheses wherever we want. We can OR whatever we want first and then OR everything else together. It really doesn't matter. So we can actually think of this as eliminating the parentheses. We don't need them. But what we can do is then rearrange these. I'm going to go ahead and rearrange them just to kind of more visually show what I'm talking about here. I've grouped the not A's and the not B's together because I want to visually show that because of the associative property, we can OR whatever we want first. We can put parentheses wherever we want first to perform the OR operation on any two values before we do it on any of the other ones. So what we can actually do is draw our own parentheses here with the like terms. And now we can figure out each of these. And I guess you don't have to do the parentheses. You could just in your mind, you can recognize that this ORed with this is going to be something. But I'm just adding parentheses to visually show it. But we can take this quantity now, and remember that anything ORed with itself is always just itself. And that same thing here, a not B ORed with a not B is just a not B. And oops, this was supposed to be a D. And then we just copy down those other terms. And that is our simplified equation. So, going back to the slides, let's see. They give us two circuits, and they want us to prove that the two circuits shown are equivalent using DeMorgan's theorem and Boolean algebra. The solution is kind of short, so I'm just going to show it on the slide here. For this first circuit, they figured out that this value, A NAND B, is here. This value would be A or B. And for this last gate, we would have to NAND the first quantity with our second quantity. And that's what they've done on this first step here. So, and remember to keep track of bars. So here we see we can apply DeMorgan's theorem. Here we can split the bar here. We flip the AND to an OR, and this quantity gets its own bar, and then this quantity gets its own bar. So that gives us this second step here. Well, there's our double bar again. We can go ahead and eliminate that double bar. Now it's just A ANDed with B. We can DeMorgan this second part here, the A NORed with B, and just make it a not A ANDed with a not B. And here's our final equation, right? For the second circuit, we have A ANDed with B, and then here we have A NORed with B, so there's a big bar over the whole thing. And then these two values are then ORed together, which gives us this here. And in one step, just applying DeMorgan to this part, we break the bar, flip the sign from an OR to an and we get this equation, and we can see that that is equivalent to the first equation. So I already talked about this concept of bubble pushing, where you change the logic gate AND to OR to AND, and then you invert the bubbles at all the inputs and outputs, meaning if there was a bubble there, you remove the original one. If there was not a bubble there, you would add a bubble. So here's just some examples of doing exactly that. And so you take an AND gate, all three of the inputs don't have bubbles, so when you convert it, you'd add bubbles to all three inputs and outputs, and then flip the AND to an OR. Second example, you would flip an OR to an and do the same thing, where you'd add the bubbles where there were none. And then the third example, flip the OR to an and. A already had a bubble, so we get rid of it. B and X did not, so we add bubbles to those, and so on. So that's bubble pushing. So just to touch on this universal capability of NAND and NOR gates that they mention here. So we can actually use NAND gates and NOR gates too, but we're starting with just NANDs. We can actually use them to, in this case, create an inverter. Because all we have to do is connect the input A to the other input, so that both inputs are A. And if we do that, if we AND A with A, and we put a big bar over it, well, what is anything ANDed with itself? It's just itself, which would then be under the bar. So now you've just created a function where the output is just the opposite of your input, A, which is basically just what an inverter does. We can then form an AND, let's say, with two NANDs, because if we take the same concept that we did before, where we know that if the input to a NAND gate is the same, if we tie the inputs together, basically, we make an inverter. Well, all we do is create an inverter to re-invert the effect, or cancel out the effect of this bubble here on the NAND gate. So you're inverting an AND function on the NAND gate already with this bubble, and then you're inverting it again with the inverter that we just described with another NAND gate, and you essentially get the regular old A and B. So then that would look, sorry, rather, if we want to implement this circuit, let's say, where we want to invert A, AND it with B, and then that whole thing we NAND with C. Well, how do we do that? We already know how to make an inverter with NAND gates. We already know how to make an AND gate with NAND gates. And we already have a NAND gate here. If the goal is to use only NANDs to implement the same logic, well, we just build an inverter with NANDs, and then we build an AND with NANDs, and we just connect them all in the same way that we do here. So then what it ends up looking like is, here's that inverter that we formed with a NAND gate. Here's these two NAND gates here. This whole thing is our equivalent AND gate, and then we connect that to the rest of the circuit, and we get the equivalent circuit here using only NAND gates. We can also form an OR with 3 NANDs. I won't get into the complicated, Boolean algebra. You could do it yourself as practice maybe, but basically we can create an OR, same effect, same function, A or B, accomplished with just 3 NAND gates connected in this way. What it's essentially doing, actually I can just draw it out real quick. What it's essentially doing is, you recognize this. This is our inverter, right? This is also an inverter. So what it's really saying is, if you ignore these 2 chips and you just assume that this is this is B, and this is A, we're essentially just making inverters on the inputs, meaning we can put bubbles here. But then you notice all 3 points on this NAND gate here now have bubbles on them. So we can apply DeMorgan's, flip the AND to an OR, and then eliminate those bubbles. And now you're left with just a simple OR gate. So this one's pretty complicated, but so I'm not going to go over it too much, but yeah, they basically just take 4 NANDs, connect them to form a NOR. This is just really showing you the universality of NAND gates. So the technique can be used to form pretty much any of the simple gates that we've talked about from just NANDs. And this same technique can also be used with NOR gates. And just as an example, you can form all of the other logic gates using only NORs, just like you could with NANDs. So we won't get into all of it, but just as an example here, here's a simple inverter where, remember that anything ORed with itself is just itself. So similar to the NAND gates, you get the same effect where you basically simplify this to an inverter. But the other logic gates can also be created with NORs. We won't get into that too much. So finally, for part 1, we're approaching the end of it here. AND-OR invert gates, or AOI gates, basically they're just they're chips that have ANDs, ORs, and inverters on them. They allow us to do things in product of sums form. So here, for example, if we're only using ANDs, ORs, and inverters indicated by these bubbles here, this is the equation that you would get from this circuit, which you can actually, these are, you notice the parentheses here, you can actually distribute them. You can use that FOIL technique to distribute everything and get this kind of equation, which gives us our sum of products form, which you can kind of represent as this, not A ANDed with C, and then our second term here, not A ANDed with not D, which is represented by this second gate here. The third gate, B ANDed with C, the third AND gate, and then B ANDed with not D, our fourth AND gate. And then because all of those individual terms are summed together, we can think of them as all going to a single OR gate. So here's just an example 74LS54 AOI chip, the AND-OR inverter chip. And we have a bunch of ANDs going to a NOR. And so, considering every single input, we can create this kind of equation here. Putting it to actual use, you don't have to use all of the gates, or you can set the inputs to ones or zeros or whatever, however you want to do it, to basically disable certain inputs that you don't want to use. We can basically use it to create whatever equation we want with A, B, C, and D. So we can, invert A and AND it with C, or we can invert A and invert D and AND it with a 1 to cancel out the effect of that particular pin, because anything ANDed with a 1 is just itself, so it kind of just ignores that pin, or we don't need to be concerned about that input. And so in that way we can kind of enable and disable the various terms in the equation that you would get from the complete chip. But the only thing you have to be careful with is that this is a NOR gate on this particular chip, the 74LS54. It does have a NOR gate at the very end, meaning there is an inversion right at the very end of the output, where if you want to cancel the effect of that bubble, you just add an inverter here at the end, and then you get your output X. So that is actually it for part 1. Part 2 we'll get into K-maps and a little bit of system design stuff, but this concludes part 1.